will tell us about Roe-type algebras and their isomorphisms, joint work with complicated co-authorship, I think.
Yeah. So, yeah, this is joint work with subsets of Baudier, Florent, Braga, Ilias, Anna Kukro, and Rufus. So George is not here, so my first joke, I will have to postpone it. Oh yeah, okay, then I should. I should wait. Well, okay. So I'm very thankful to the organizers for having me. It's good to be home. I spent in this building the most hours of my PhD, which was 5 years. So okay, George is not here. Whatever. So I made a quick math while flying here, and if you count the person who has spent the most hours 5 meters within myself in the last 15 years, there is my wife, my daughter, and George. and only because I sleep with my wife and my daughter. If not, there is George above. For 5 years, I spent from noon to 10 p.m. my time in my spot, which is like here, and George's spot was 2 meters from me. So we shared a lot of oxygens. Wow. All right. Let me start with some decent stuff. J. Mary was a mathematician, very young, in Zurich. He actually suddenly died last year, but in his notes of algebraic topology, he has the following list, and he says topology is hard. Algebra is easy. Algebraic topology takes problems of topological nature and translates them into problems of algebraic nature. Profit. That's what he says. So now I have a similar approach in my talk. This is coarse geometry. Coarse geometry, it's hard. Operator algebra, it's obviously easy. Roe-type algebras, they take coarse geometry problems into operator algebraic problems. Profit. Okay. So I guess we all know what this is. I should tell you a bit of what that is and on what these are before going to the second part of my talk, which is isomorphisms. So coarse geometry is the study of metric spaces from far away. So you take a metric space and you walk back a lot, and you look at how the space looks like. So in particular, the maps that we care about here are coarse maps. So let's fix two metric spaces. This is a delta, obviously. A function from x to y is coarse if it maps close points to close points, or you can write it as for every r, there exists an S, such that if you give me 2 points in x, which are close, well, f, it's, the distance between f of x and f of x prime, it's small, okay? So, and this choice is uniform over your choices of x and x prime. And two maps from x to y are close if when you walk back, you don't see the difference between them, meaning that the supremum over x in x of the distance calculated in y between f of x and g of x is finite. Okay. So what is a coarse equivalent, which is really the maps we care about here? A coarse equivalence is a coarse map coarse equivalence. Coarse equivalence is it's a coarse map such that there exists a coarse G from y to x, such that when you compose these two guys, they're close to their respective identities. I will be wrong about domain and codomain, but this should be domain of identity on x. This is close to identity of x, and this is close to the identity on y. So coarse equivalencies basically allow you to take a metric space and discretize it. Okay, so we are only going to care about discrete spaces. In fact, we are going to care about very discrete spaces. So definition, a metric space X, it's uniformly locally finite. Locally finite, or ULF, ULF, as Braga says. If, well, not only balls are finite, but they're uniformly finite depending only on the radius. So that means that for every given r greater than 0, the sup of the size of the ball of radius r around X is finite. And an example of these can be, okay, well, finite sets. And they're all course equivalent, obviously. But also like Z squared, or more generally, if you give me a finitely generated group, so G is a group which is finitely generated, then you can consider the Cayley graph and the shortest path metric, and that's a very good ULF space. In general, just take any graph of finite degree and take the shortest path metric. So Cayley graph of G with shortest path. So this is an example. Another one is discretization of things we like Zn is a discretization of R to the n, but most generally for smooth Riemannian manifolds, you can discretize those guys and get uniformly locally finite spaces that are approachable by coarse geometry. So discretization of stuff. And also you can get these weird expander graphs or families of expander graphs that I'm going to mention like now and then maybe later, but expander stuff. And these are more complicated objects than for example, these guys. But they arise and they're related to like, well, the coarse geometry of groups is something that Misha Gromov worked a lot on. So these are our examples, main examples. And now, yep. Okay, so this is essentially coarse geometry. And now I should tell you what Roe-type algebras are. These objects were introduced by John Roe in the late 80s, early 90s, essentially for index theoretic purposes to treat Riemannian manifolds. Okay, this was the original motivation at the beginning. But then later on, they were used in a lot of applications in operator algebra theory and outside. There is a very nice, tough to read if you don't know math physics, but there is an article on Archive by Ludewig, which is the entry of the Encyclopedia of Mathematical Physics, which talks about applications of coarse geometry to mathematical physics. It's a tough read if you don't know math physics, but it's also interesting, like, because you can see what people are doing with the objects you like. So let me just introduce Roe-type algebras, or at least the three of them that I'm gonna need for this talk. So, well, first of all, from here, notice that X is countable, okay? Because it's a metric space and balls are finite, so this is a countable space. So that means that we can construct a very nice Hilbert space, which is a separable Hilbert space, which is L2 of X. And notice that here we do fix a base. Okay, so the base is going to be fixed. It's going to be the delta X. These are just the function that sends little x to 1 and everything else to 0. This is an orthonormal base. And the fact that we fix a base, it's important for our definition, because now once you fix a base, you can look at operators as just x by x matrices, and in the x prime entry, you just put the inner product. It's a complex number. And now for an operator in B of L2 of X, I define its propagation. This is just going to be a number, and it's going to be the supremum over x, y in X, of the distance between x and y, but I'm only considering those entries where A takes a non-zero value as a matrix. It's not zero. So if you think of like these as the naturals, here you're just looking at banded operators. So often these operators are, operators of finite propagation are really referred to as banded because it means that, this is the naturals with the usual metric. You just put a band around the diagonal, and then you take everything. When you consider the operators of finite propagation, they form an algebra. This is just the closure. The uniform row algebra of X, it is the closure of the algebra of propagation, finite propagation operator. So a few things that you might already see is that every diagonal operator is of propagation 0, actually if and only if. So there is a canonical copy. So this is uniform row algebra of X. There is a canonical copy of L infinity sitting here, and it's the diagonal operators. And there are also all the compact operators. All compact operators you can approximate with like finite stuff up to epsilon. So since I'm closing in norm, well, I do get the compacts are there. And these can actually be all sometimes. So yeah, okay, yeah. I'm not gonna say it anymore. Everything is wolf.
So where is wolf being used?
Oh, well, because if it's not wolf, then you might have unbounded operator once you, so the point is like you can construct an unbounded operator of finite propagation. But it's not in B of H anymore, but it sees parts of your course structure, but you don't get it this way once you consider B of L2 of X.
But you can unbounded operator in L infinity. You can think that way. And we can just say bounded operator.
No unbounded operators in L infinity.
But I mean, you know what we mean. You know what we mean.
He's not wrong.
But does this definition not make sense? If X is not.
No, you can take the same definition, of course, but then the structure will not, the sister algebra will not recover all the information that you want about the space. Already here you have to prove it that it encodes, but some information will get lost, and you don't want that. Okay. So, in fact, is that you can see a sister U of X as being generated as a sister algebra is generated as a sister algebra by partial bijections between subsets of X. Okay. So meaning that you take two subsets of X and a partial bijection, you just put finite propagation. Sorry, that's bad. Of finite propagation. So you take two subsets and a bijection of partial bijection of finite propagation between them, and you just write the matrix where 1 is the entry where X goes to Y. You write 1 in the XY entry. These operators as bounded operators, they do generate sister U of X as a sister algebra. So as I said, there is L infinity there. So this is 1. And this is the compact. And there is the compact is there. They're all here. But this could be all. For example, if you take the space of all squares of natural numbers for n in, this is logic day, omega. Just take this space. That's exactly, the uniform row algebra of this space is exactly generated by L infinity and the compact, and you get nothing more. Because every other partial bijection, if it moves more stuff, it cannot have finite propagation, because this somehow, the distance gets bigger and bigger. So the propagation will get huge. Okay, so this is the uniform row algebra. The second algebra I'm going to care about is the uniform row corona. Means that I have this lovely ideal there, which is the compacts, and I quotient by that. So the uniform row corona of X is, by definition, is Q star of X, which is the quotient, history of X, by the compact. And the third one, it's its center, which is called the Ikson corona of it. Now, the Ikson corona was defined as taking functions which are slowly oscillating on X, and then quotienting by C0, because C0 of X is there. On the other hand, you can just realize it as the center of this. This is a theorem. It's a proposition. It's a fact. But the center of it, it's the Ikson corona of X. You can take this as a definition, or you can take it as slowly oscillating or Ikson functions. This was not introduced in these terms. I mean, it was introduced as slowly oscillating mod C0, and it was used to relate coarse cohomology with usual cohomology. This was a tool that was used, I guess, by Ikson and Roe to make that connection between the check cohomology of the system algebra and the coarse cohomology of the space. So this is the center, and now which is Ikson corona. And now the point it comes here of this word, but the real point is like how much geometry of X can I recover from these three objects? I mean, if I know information about the uniform row algebra, what can I tell about the space? If I know information about the corona, what can I tell about the space? And if I know information about the Ikson corona. So let me just say, okay, this one I should not use. This one is okay. So I want to know if the two, well, the easy part, it's like if the two spaces are similar, what about the algebras? And the difficult part is like if the algebras are similar, what about the spaces? So first of all, notice that if X, I'm going to omit the metrics. If X and Y are bijectively coarse equivalent, so if there is a coarse equivalent, which is a bijection, coarse equivalent, then the two uniform row algebras are isomorphic, and they are isomorphic, but just the isomorphism is very easy to realize. You just take the bijective coarse equivalence. You construct a unitary between L2 of X and L2 of Y that sends delta of X to delta of the image, and that works. Okay. For the coronas to be isomorphic, well, as we know, for coronas, we're taking out C0 compacts, so we can forget about finitely many points on one side and on the other side, because, well, the coronas don't see that. So if X and Y are bijectively coarse equivalent up to finite sets, then the coronas are isomorphic. Y, I guess there was a U. And lastly, and I don't know, so these are easy facts, needs no attribution, but the fact that coarse equivalence implies if X and Y are coarse equivalent, then the Ikson corona of X is isomorphic to the Ikson corona of Y. This needs a proof, but I don't know who gave a proof. It's in John Rawls' book. and it doesn't say if it is proof. It's not a complicated proof, but it's more complicated than one line. Maybe it's 2 pages, even less. Anyway, coarse equivalence implies that the Hickson coronas are isomorphic. So more generally, there are, so one would like to revert these arrows, of course. I mean, the ultimate goal is to say, okay, I can recover projective coarse equivalence, this up to finite sets or whatever, just by looking at the algebras. This is the ultimate goal. But in general, what one can ask what kind of geometric properties of the spaces get understood by the algebras. And so I'm going to put out a bounty, because Andrea had a good idea of doing so. So one information that is still not clear talks about the nuclear dimension of these sister algebras. So first, let me just say that there is an amenability-like condition on the space. It's a regularity one that tells you that that holds if and only if the sister algebra that I defined is nuclear. So the uniform row algebra is nuclear if and only if whatever. But this amenability-like condition holds in particular for spaces of asymptotic finite dimension in the sense of Gromov. So we have like spaces X of asymptotic, so bounty. Well, pre-bounty. Pre-bounty is X is asymptotic finite dimension. Now, okay. Fact. If F has finite asymptotic dimension, implies that the nuclear dimension of sister U of X is finite. What is it? So the bounty is like, are these two equal? Is the asymptotic dimension of X in this case, so in case of finite asymptotic dimension, equal to the nuc dim? One direction it's known by Wilhelm and Zacharias. So it is known that this is less or equal than that. And it's also known that like some cases, some low cases, 0, 1, and things like that are known. But it's not known in general. I have to say that Liao, Kangli, and Wilhelm Winter recently posted a paper called Diagonal Dimension. And in that case, they actually, these two things coincide. But the diagonal dimension takes in its definition the maza, a Cartan maza, which is our copyable infinity. So since you now have the Cartan maza in your hand, now the fact that the diagonal dimension and the asymptotic dimension coincide is, well, it's easier. The head is Z squared. We do know that this, so Z squared with the usual metric. We do know that this one has asymptotic dimension 1 or 2.
You know it's got asymptotic dimension 2.
Asymptotic dimension 2, yeah, because there is a 2, yeah. Nuclear dimension 1 or 2, which one is it?
My guess is 1.
Yeah, my guess is 2. But so no. Is it 1 or 2? Yeah.
Is the reverse arrow the fact
I am not
Don't see why.
sure. No, I mean,
So in the boundary,
it's not known.
assuming that we're starting with that.
Assuming we're starting with finite. I mean, which one is the big one? This one. This is finite. No, yeah. I mean, I guess Rufus also told me that they could all be 1. But yeah, who knows? Okay. But let's go back to the isomorphism problem, which will be because it's a problem where I actually have something to say. Right. So the first attempts to the isomorphism problem, I guess they go back, the first successful attempts for the uniform row algebra, they go back to Spakula and Willett So the idea is the following. The main idea that they had is the following. So fix two spaces, x and y, fix an isomorphism between the uniform row algebras. And now, let's look at the canonical copy of L infinity of x that you have inside the domain, and let's look at where it goes. Now, if we are starting with an isomorphism coming from a bijective course equivalence, every element of this guy goes to an element of L infinity of y. In particular, the minimal rank 1 projections, delta of x will go to delta of y if it's coming from f, okay? And now you can construct the function, just send x to y, and it's gonna work. The point is like, so if this one is inside here, well, it must be equal, then you know what to do. You just send x, the minimal, you look at where the minimal projection goes, it's sum delta y, send x to y, you're good. But now what if this doesn't happen? How do you pick points? Because what you want ultimately is to construct a function from x to y. You want to prove that these guys are coarsely equivalent, bijectively coarsely equivalent, similar in some sense. So you want a function from x to y. And how do you obtain it? Well, as I said, if this happens, you have a point here, and you're mapping it to another point there, okay? But in general, this is not true. In general, if this does not happen, you have a point here, which is a rank 1 projection, and it gets sent to something like this, right? I mean, it's a finite rank, I mean, it's a rank 1 projection. So it's essentially a finite matrix. But now here, these are your candidates. Like you want to send the point x, this is on the diagram. And this is definitely not a diagram, but yeah. You want to send your point x to somebody here. But you want to do it so that when you pick, you get a course equivalence or a bijective course equivalence or something. And now the point is to do it in some uniform way. So because this matrix might not leave a trace, if x goes to infinity, maybe this gets bigger and these values get smaller. And this is a problem because then the map you obtain, well, you don't know how to construct it. So if you can actually have a trace of the image, this is phi of chi is the projection onto delta of x, chi of x. This is this guy. So you want this trace to be big uniformly, okay? In particular, let me define for delta greater than 0, let me define the set y x delta as all the y's such that the norm of phi of chi of x, chi of y, or I guess you can delta of y, is big, okay? So this is just, you give me delta and I look which entries are reasonable, okay? And the point is like, so this depends on phi, but I'm not gonna add another index here. But the point is like that if there exists a delta such that yx delta is non-empty, and also the other ones, but I think once you get those, you get the other ones, but let's say x, y delta. So these are just defined in terms of phi minus 1, okay? But if the delta is uniform, such that all of these guys are non-empty whenever you range x over x and y over y, then if you just pick any element, you associate to x any element of this guy, that's a course equivalence. So if x gets mapped, well, f of x belongs to y of x delta, this is a course, f is a course equivalence, and you're good. You got a course equivalence. Now let me also say that, again, in property A cases, you actually get a bijective course equivalence. This was done by Stewart and Rufus using the operator norm localization property. In a it's a very analytic property, but they use it very sneakily. Very nice argument. And you do get bijective course equivalence for property A spaces. Now, why is this true? So F is a course equivalent. F.
The course is associated to y any element of x by y.
Yeah. Now the point, so it's to get these guys non-empty. Okay, I want a single delta such that all of these guys are non-empty. And again, in the property A case, Rufus and John Rowe showed, well, Rufus and John Rowe showed that having property A is equivalent to not have certain ghost operators. And if you don't have ghost operators, it's fairly elementary to show that all of these guys are non-empty. Okay, so let me see. So basically, let me get the story straight. Row, we let property A equivalent, which is nuclearity of C star U of x, equivalent to no ghosts or certain ghosts. And now, and then spacula and we let show that if no ghosts, then all the yx delta, so there is this delta, such that yx delta is non-empty. Okay. So this, I guess, is the story, how it goes. So basically, the main point of the, the main task left is to find this delta such that these guys are non-empty. Okay? And this was done online during pandemic by BBFKW. Am I missing? No, and myself. Haha. BBFKBW. Yeah, there is delta such that yx delta is non-empty. And so, if C star U of x is isomorphic to C star U of y, then x and y are coarsely equivalent. Coarsely equivalent. Now, getting bijective course equivalence is tougher.
So the preamble to the theorem was that this was known
for certain spaces.
And now you're saying this is just always true.
Yeah, it's unconditional.
Okay.
Yeah, I mean, there is a story here. You keep putting geometric conditions which are weaker than property A. I think Braga and Ilias had something to say there. But this is unconditional on the spaces. I mean, these are ULF metric spaces, blah, blah, blah. Now, okay, let me just say two things. First of all, it's very nice how we prove it. I'm not going to say anything more than two things, which is we use a lot of equiapproximability results, which ultimately goes back to the fact that Braga is smart. And then, we also use a result, a quantitative result on approximate convexity of the range of certain vector measures, which goes back to a theorem in economics of Shapley and Folkman. And this, yeah. So this is, I'm not going to say more about that. But as I said, in the property A case, Stewart, okay, Stewart and mainly Rufus, sorry, Stewart, you proved that you can get bijective course equivalence from isomorphism. Okay, so you can get a bijective map. They use this operator norm localization property. And then recently we did it for other spaces, especially for expander, for spaces coming from expanders. And this recently was done by two Bs, Farah, myself, and Rufus. Okay, so we get it also for other counterexamples that are not property A, but we don't have a general result in full. Yet this was very nice for us, especially as it was done online, and one of the people there, I guess Anna, was very pregnant when this happened. We were all locked down. I had a small baby. Florent had 2 babies around. It was ridiculous. We had a square meeting online in 5 different time zones. It's surprising that we got something out of that. But okay, I guess I should go to the other 2 algebras, which is where set theory comes in. So uniform row algebra case, it's, well, the things I know are there. What about the uniform row coronas? So Q star U of X, isomorphic to Q star U of Y. I remind you that this is a quotient of the uniform row algebra by the compacts. And now the problem is like you don't have a copy of L infinity to work with, because the copy of L infinity became a copy of L infinity of X mod C0 of X. And this all sits in the Calkin algebra. So now you have phi of this algebra here in the Calkin algebra. And if you know a tiny bit of set theory, you know that this is a mess. In particular, you might not be able to lift. That's the problem. You might not be able, so you have and now you have an infinity here, but you might not be able, this is B of H, Y, I guess. This is phi, restricted to this copy. This is the usual thing. You might not be able to find a suitable lift. And in fact, under continuum hypothesis, you can construct copies of L infinity of C0 inside the Calkin algebra, but also inside here. I mean, inside another copy of L infinity mod C0, which does not admit a star homomorphic lift. And now, if it doesn't happen, that's a problem, because I don't know where to send little x. I need to have a suitable lift. So under continuum hypothesis, I cannot lift. But, well, fortunately, when this problem was given to me, I was at Fields, and Ilias and Braga talked about this, and I was like, okay, but I have a theorem that can help you. So theorem by Paul McKenney, who now works at Google and makes money, and myself. So assume, let's see, I need to get my axioms straight. Yep. Yeah.
But like, I'm just curious how you came across this.
It's a theorem about vector measures that they use in economics. So yeah, Ilias studied vector measures at that point. No, I mean, we were like, we had a baby case, we had a test case that we wanted to solve, which is the expander built by Scandalis, Laforgue, and Nixon, I guess, and Nixon. And so we solved that case by hand, and then we started to work on, like, we had a statement on vector measures and convexity of vector measures, and then we located the right theorem. I mean, there is work to do. It's not just theorem and then it works. But we had a test case, of course. Okay, so assume ST EPD WTHA, which is some set theory you probably don't want to hear about. These are axioms known as forcing axioms for the experts. This is the usual blend of OCA and MA, or maybe less, but these are incompatible with the continuum hypothesis, obviously, because that what I'm going to state is not true under continuum hypothesis. They imply the continuum is Aleph2. And these were, I mean, these are pretty natural axioms for a set theory, for a set theorist to work with. And they are, like, you don't need large cardinals to get the consistency of these axioms. And that are not called some set theory you probably don't want to hear about officially. But let phi from L infinity of x, from L infinity to the Calkin algebra be a star homomorphism. Then you can lift L infinity mod C0. Then there exists psi from L infinity to B of H this is the usual quotient map. This is the usual quotient map. You can lift, which is a strongly continuous star homomorphism. Now, you're not going to be able to lift on all elements. Yes.
But you get some continuous belief because you can have some stupid thing that prevents it from continuity. Some alpha filter or limiter.
But I'm not lifting on everything. I didn't finish. Which lifts on a lot of elements. And now I'm not going to bother you with this because in the case where we are interested in, it's all. It lifts, period. But that should answer your question. Well, your remark. I mean, it lifts on functions supported on a certain nomic ideal. Okay. Elements. But for this application, so when we are in this case, so we have an isomorphism of uniform row coronas. We look at the restriction to the canonical image, the canonical maza, which is the image of the maza in B of H. And here, a lot of elements, it actually implies all elements. Not the same lift. You have to modify your lift a bit, but that's okay. You can find the lift which lifts on everything. And then, if you apply this theorem, you juggle a bit, and then you obtain what you wanted to. I mean, you obtain, this is Braga, Ilias, and myself. So what you get is precisely that if assume set theory, if the uniform row coronas of two ULF spaces are isomorphic, then X and Y are course equivalent. And moreover, if X and Y happen to be two of the spaces that you had, like with either property A or where you could get bijectively course equivalence, you do get, so in good cases, you get that they are bijectively course equivalence up to finite sets, because you still have to remove finite sets.
Did you have the up to finite sets of the general state?
No, because course equivalent is up to finite sets. Just course equivalence in itself. You can map 5 points to whatever you want and still a course equivalence. Yeah, this course geometry doesn't know what's happening. And that's why, especially the Higson corona is very useful because it helps you deal with the spaces of n's, so with sequences that go to infinity. Up to finite sets. Now, I do not know whether you need set theory here for this statement. But for the fact that you can lift, you do need set theory. This I can prove. So the third, yes, that's good. The third algebra I want to talk to you about is the Higson corona. And this is the new stuff. So, okay, now what we want to show, it's like what we want to get is like we have an isomorphism between the Hickson coronas of two spaces, x and y. What can we say about the spaces? But now the theory really causes issues because, so okay, let me remind you, this is the Hickson corona, but Protasov showed that under CH, if x has asymptotic dimension 0, and I guess I should say, and it's infinite, because one point has asymptotic dimension 0, then the Hickson corona of x is isomorphic to L infinity mod C0. So now a Protasov proof uses topology, but topology is hard. So we use operator algebras for this proof. You just prove that the Hickson corona is real rank 0, countably saturated, of the right size, and no minimal projections. And all of those guys are elementary equivalent. And so under CH, they are isomorphic. So under CH, you have no hope. You have many spaces that have asymptotic dimension 0 and that are not coarsely equivalent. So you have no hope of recovering the space. But we live in a good world, which is some set theory you probably don't want to hear about. And therefore, well, we just have to look at our theorem of me and Paul McKenney and figure out if we can modify it. Fortunately, we already had modified it. But first, let me just tell you what I want to do. Because, so, okay, the theorem that I can state is the following. There are two theorems. One which I wrote, the other one which I didn't write, but it's a theorem, I think. If sister u of x is isomorphic to L infinity of x, L infinity mod C0, then x is coarsely equivalent to the space. The Hickson corona. Then if I'm isomorphic to L infinity mod C0, then I am the squares. I'm coarsely equivalent to the squares. Okay? So which give naturally L infinity mod C0. But the real theorem, which is the one that I didn't write, is that assumes a theory. If C nu of x it's isomorphic to C nu of y, then x and y are coarsely equivalent. All right. No. No, come on. That'd be too easy. How do I do it? Let me. You're going to say, of course, after I tell you how do I do it. You were a nice advisor. Okay. Oh, come on. Kidding.
When you say set theory, though,
It's always the same.
but anti-CH, the Protasov result is CH.
Yeah. Yeah. Set theory, it means some set theory you don't want to hear about.
Right, but like the Protasov result says, like if the Hickson corona is isomorphic, sorry, if the conclusion of the Protasov result is your assumption of the next theorem.
Yeah. So basically here it says that all spaces of asymptotic dimension 0 have isomorphic Hickson coronas. So you have like isomorphism where the spaces are different under CH. But now I'm not assuming CH. I mean, it's hidden here. And it says, well, actually, no, Hickson corona does distinguish. So if you are, if I am isomorphic to you, we are the same space. So no, they should not contradict each other, these two theorems. Okay, so how do I do it? Well, let's assume for a second that X is a disjoint union, coarse disjoint union. That means that these are finite pieces and they go away from each other, meaning that one is here, then there is one there, and then this distance gets big. So the distance between xn and xm goes to infinity as n plus m goes to infinity. So they're really, really spread like butter, and they're all finite. Okay. Now suppose that you have a sequence xn, where xn is in the nth block. So we have our spaces, 1, 2, 3. Now I have a sequence of points. And now what do? I will construct functions which are Ikson functions, or slowly oscillating functions, okay? Which essentially do this, which are 1 at xn. So there exists a function f such that f of xn is 1. And well, it's a blob, but it gets more slowly oscillating, right? Because you want it to be such that pi of f belongs to the Ikson corolla. Pi of f is the map under the Kalkin algebra. And now, x. Now from this one, by cutting with characteristic functions on xn, or characteristic function of some xn's, I do get a copy of L infinity, which is not a star homomorphism, but is an order 0 map. It's a positive order 0 map. And so I get a positive order 0 map from L infinity mod C0 inside C star nu of x. Just how do? I take a subset and I cut by xn for n in that subset, my function f. Okay? Now, though, the good thing about, oh yeah, I guess, so this is here, but then I apply phi to this, of course. The good thing is that this theorem here does not need this. It only needs orthogonality preserving and linearity, which we have, of course. Preserving, of course, here you get orthogonality preserving, and I guess linear, and you get linear. So now I can apply this theorem here to phi of this copy of L infinity mod C0, and I do get a local lift on this sequence xn. And now the only thing that I'm left to do is to glue together all of these things. This needs some work. I did write it in case, because I wanted to check it was working. So I did write it in this case, and this is fine. Or in case of asymptotic dimension 0, in fact, I did write it because these are projections and writing is much less painful. But it's an OCA gluing uniformization argument that, well, up to epsilon should be able to write down. So you do get, once you have these local lifts, for every sequences that go to infinity, you do get that you can glue them together and get a full function from f from x to y. This is in the case of coarse disjoint unions, but the general case is not more difficult than this. And with this, I should thank you.